Ever wonder what keeps satellites zooming around Earth? Or how astronauts float like magic in space? Hi everyone, I am Atom, and together we will explore the physics behind orbital velocity, escape velocity, the inverse square law, Newton's Universal Law of Gravitation, and the secret to weightlessness. Orbital velocity. First up, Newton's thought experiment known as Newton's cannon. Imagine a cannon on top of a very tall mountain, so tall that it is above the Earth's atmosphere. If you fire a cannonball at a slow velocity, the cannonball will curve down and fall closer to the mountain. If you fire it faster, it will curve further and fall further away. As you keep firing the cannonball faster and faster, it will go further and further around the Earth and then hit the Earth. But at a certain velocity, it won't fall back to Earth. Instead, it will keep orbiting the planet like a satellite. This is called orbital velocity. To stay in orbit around the Earth, you need a speed of about 7.8 km per second. Here is a fun fact. The James Webb Space Telescope orbits the Sun near the second Sun-Earth Lagrange point, L2, roughly 1.5 million kilometers from Earth, tracing a halo orbit around L2. This orbit allows Webb to stay aligned with Earth while avoiding direct light from the Sun, Earth, and Moon, providing a stable environment for its infrared observations. Escape velocity is the velocity you need to break free from the gravitational pull of a planet, moon, or even a star. For Earth, escape velocity is 11.2 km per second. When an object reaches escape velocity, it keeps moving outward forever, unless another gravitational force pulls it into its orbit. As the object approaches escape velocity, the shape of the orbit changes. At speeds lower than 7.8 km per second, it will fall back to Earth in a curved trajectory, that is paths A and B. At 7.8 km per second, it stays in Earth orbit, and that is path C. Between 7.8 and 11.2 km per second, it enters elliptical orbit, and that is path D. And at 11.2 km per second or greater, it escapes the Earth's gravity pull, which is path E. But wait, there's more. Escape velocity of the solar system. A spacecraft launched from Earth at 42 km per second has enough velocity to overcome the Sun's gravitational pull, allowing it to escape the solar system. This is where Pioneer 10 comes in. Pioneer 10 launched on March 2, 1972, from Cape Canaveral aboard an Atlas Centaur rocket, achieved a launch velocity of about 14 km per second relative to the Earth. It was the first spacecraft to cross the asteroid belt and reach Jupiter. During its closest approach to Jupiter, Pioneer 10 captured some iconic photos and detailed data on Jupiter's intense radiation belts, magnetic field, and atmosphere, including its great red spot. Jupiter's massive gravitational field acted like a slingshot that accelerated Pioneer 10 and allowed it to escape the solar system. Aboard Pioneer 10 is a gold anodized aluminum plaque with Earth's coordinates and images of a man and a woman. The lines on the left show the positions of 14 pulsars pointing to our sun as the home of our civilization, with binary numbers representing their frequencies. At the time Pioneer 10 was launched. The hydrogen atom, shown in the top left, acts as a universal clock and yardstick, helping other civilizations understand the timing and size of what is shown. The right side has human figures, 64 inches tall, created using the hydrogen wavelength as the scale, along with planets and the spacecraft's path passing Mars and Jupiter. The plaque was designed by scientists Carl Sagan and Frank Drake, and the artwork was drawn by Linda Salzman Sagan. The information on the plaque is a kind of hello for extraterrestrial beings, just in case they want to find us. The spacecraft officially ceased science operations in 1997, with its last faint signal received on January 23, 2003, when it was approximately 12 billion kilometers from Earth. Now, Pioneer 10 is cruising silently toward the constellation Taurus, with Aldebaran on the itinerary in about 2 million years. Inverse square law. Imagine running a restaurant where the sole menu item is peanut butter on toast, served with the flair of a peanut butter gun. To butter a toast for your very first customer, let us make believe you stand 1 meter away from the toast and push the butter gun. Let us say it spreads 1 millimeter thick peanut butter on the toast. So, when distance d equals 1 meter, the number of slices is 1 and the thickness of the peanut butter is 1 millimeter. 4 customers now arrive for breakfast. You keep the butter gun 2 meters away. You notice that it covers a wider area so that you can lay out 4 slices of toast as shown. You push the butter gun and it shoots the same amount of butter as before, but now it covers 4 or 2 square slices. So the thickness of butter equals 1/4 millimeter or 1/2 square millimeter. So when distance d equals 2 meters, number of slices is 4 or 2 square, and the thickness of the peanut butter is 1/4 millimeter or 1/2 square millimeter. Challenge question. 9 customers arrive for breakfast. How far away should the butter gun be from the toast? How many slices would the butter cover in one shot? What will be the thickness of the butter on the toast? If the butter gun is moved 3 meters away, following the same pattern as before, the butter should cover 9 or 3 square slices. So the thickness of butter will be 1/9 millimeter or 1/3 square millimeter. So the general rule is, if the butter gun is moved d meters away, d square number of slices can be covered and the thickness of butter will be 1/d square millimeter. And this is the inverse square law in action. Just like the signal of the Pioneer 10 and the thickness of peanut butter, gravity's pull weakens with the square of the distance. So, let us dive into Newton's Universal Law of Gravitation. Newton showed that the same gravitational force that pulls an apple toward the Earth also keeps the moon in Earth orbit. Newton's Universal Law of Gravitation tells us that every mass in the universe attracts every other mass with a force. And this force is directly proportional to the product of their masses. So we can say Fg is proportional to m1 times m2. And this force is inversely proportional to the square of the distance between their centers. So Fg is proportional to 1/d square. Combining these two relationships, we get Fg is proportional to m1 times m2 divided by d square, where Fg is the gravitational force in newtons, m1 and m2 are the masses of the two objects in kilograms, and d is the distance between their centers in meters. To make it a proper equation, we include a constant, big G, called the Universal Gravitational Constant. So now the equation would look like this. Fg equals big G times m1 times m2 divided by d square. Newton did not calculate the value of big G. That was determined much later by another British scientist, Henry Cavendish. Cavendish used a torsion balance to measure the gravitational force between lead spheres. His experiment was so precise that it determined the value of big G. Big G equals 6.67 times 10 to the negative 11 Newton meter square over kilogram square. This small value of big G shows that gravity is a weak force. In fact, gravity is the weakest force in nature. But we feel Earth's gravity because Earth is so massive. Mass of Earth is about 6 times 10 to the 24 kilograms. Now let us move to weightlessness. Imagine being on a drop tower ride at an amusement park. Securely strapped in, the ride slowly lifts you to its peak. Then, without warning, it releases, sending you plummeting downward. Your body's inertia resists the sudden change in motion, wanting to continue upward as the seat drops. For a brief moment, you lose contact with the seat, leaving no support force acting on you. You feel weightless. This feeling of weightlessness arises because in that moment, the support force that usually holds you up is completely absent. Ever wondered why astronauts feel weightless in space? It is not that gravity disappears in space. Gravity is always there. Weightlessness happens when you are in free fall, just like astronauts in the International Space Station. The only force astronauts experience in space is gravity force. So the key to weightlessness is the absence of a support force. This lack of support force creates a sensation of weightlessness. Now imagine standing on a bathroom scale inside an elevator at rest. The scale measures the support force exerted on you, which equals the gravity force. You feel your normal weight as you push normally on the scale springs. When the elevator accelerates upward, the support force exceeds the gravity force due to the upward net force. The scale shows a higher value and you feel heavier than normal as you push harder on the scale springs. When the elevator accelerates downward, the support force becomes smaller than the gravity force due to the downward net force. The scale shows a lower value and you feel lighter than normal as you push less on the scale springs. If the elevator cable breaks and the elevator enters free fall, the scale reads 0 because both you and the scale fall at the same rate, leaving no support force to measure. You exert no push on the scale springs, and at that moment you feel weightless. Challenge questions. 1. What happens to the gravitational force between two objects if the mass of one object doubles? 2. What happens if the distance between two objects is tripled? 3. If both masses double, how does the force change? Research question. Research about the life and contributions of Henry Cavendish. Please subscribe, like and share, and I'll see you in the next science adventure. Happy learning. Thank you.